is Dr. soon-to-be Dr. Mr. soon-to-be Dr. Edinah Gnang, who will speak about on two semi-positional recursive integer encodings.
All right. So thank you, Dr. C, for having me give a talk at the experimental math seminar. So this is a project which started 2 years ago in Dr. Z's experimental math class, and that year the theme was number theory. And I was lucky to be given the opportunity to pursue the research at Microsoft. Microsoft Research in New England under the supervision of Professor Henry Cole. And the goal really is to try and beat the decimal system, the decimal encoding system. So that's broadly the goal. It seems overly ambitious, and I want to argue we're halfway there. Okay. So how do we start? So on March 19, very important day. So March 19, 1997, Professor Doron Zeiberger wrote Opinion 14. So the Opinion 14 states, it's time to kick 0 out of the elementary curriculum. All right, so presumably, and I'm taking this from the opinion, if you want to do 109 times 19, and if, just like me, you struggle to explain to your kids the algorithm for multiplication, you can realize, as suggested by the opinion, that things become much easier if you use t for 10, so this is t times t plus 1. All right, so if you use t for 10, you essentially skip the 0. And the operation of doing multiplication for integers essentially equate to polynomial algebra. So the opinion concludes by saying it's better to work in base 2. The reason for that is the alphabet is smaller. You don't need a letter for 1, 2, 3, 4, 5, all the way up to 9. You don't need 0. And he says if you work in base 2, you should also skip 0. So the best place to start is with integer arithmetic base 2. And since I'm a computer scientist, I have a special appeal for integer arithmetic base 2. So the argument is if you're doing arithmetics base 2, you're essentially doing polynomial algebra mod, so modulo x minus 2. Okay, so what do I mean by that? So an example may make things clearer. So let's say we're looking at the number 5. So 5 in base 2 is expanded as 2 squared plus 1. And to emphasize that I'm doing polynomial algebra, every time that I'm going to write the 2 for the base, I'm going to substitute it for the letter x. All right? So this I will write instead as x squared plus 1. And if you want the number, you should plug in 2. Is it clear so far? Questions are welcome during the talk. I mean, it's more important to me that you guys understand what I'm doing than to me to finish.
You say your objective is to kick 0 out of the curriculum, but now to base 2, you're still working with 0 and 1.
So, agreed. I will tackle that question by the end. So the opinion says we should kick 0 out. I don't claim that I succeed at that goal. I think the goal is noble. I see merit to it. But my goal for this talk is to argue you can do better than the decimal encoding, in some sense. And I'll try to make that clear. All right, but here already you see we get some mileage. By writing things this way, if I were to write this in base 2, what would I have written? I would have written the string, so let's take a bigger string. So let's say I'm writing now 7. 7 would be written as the polynomial x squared plus x plus 1. And if I want to do the multiplication 5 times 7, well, this is where the carry comes for free. Plus x plus 1. Okay, so the argument is, if I could explain polynomial algebra to my daughter, I wouldn't have to worry about explaining the difficult algorithm with carries and so on. And why is that true? So the example is illustrated by expanding the polynomial to get the following. So x to the power 4 plus x cubed plus 2 x squared plus x plus 1. Now, I said you're doing polynomial algebra. I should have been careful to specify where the coefficients come from. So the coefficients are in the semi-ring. So this is not a ring. It's a semi-ring because I don't have additive inverses. The coefficients can be numbers. But the rule is every time you see a 2, you're allowed to change it for an x, if it's at the coefficient level. So here's what I mean. So here we have a 2. I want the coefficients to be just 1. So I'm allowed to change the 2 into an x. All right, so then I would get the following. X to the power 4 plus x to the power 3 plus x times x squared plus x plus 1. So right away, I see that this is going to become x cubed. Let me write x cubed. And I'm back to a situation where 2 appears now as a coefficient here. So I have x to the power 4 plus 2x cubed plus x plus 1. And now I do the same trick. Every time I see a 2, I'm allowed to turn this into an x.
2x cubed.
2x cubed, thank you. Thank you. 2x cubed. I'm allowed to change the 2 into an x, so as to get x to the 2 times x to the power 4 plus x plus 1. But then I'm done here because I have x to the power 5 plus x plus 1. Okay, so now I'm ready to compare this with the base 2 encoding and argue that, we've skipped the zeros. Right? So if I were to write this in base 2, the string would look something like this one. So 1, 0, 0, 0, 1, 1, and this is the string in base 2. So being able to write things as polynomials allowed me to essentially skip these zeros, and it gave me something else. It gave me the fact that the positions here don't matter much. The positions of the terms. So if I were to write this as follows, you still get the same number. All right, so that's why I'm calling this semi-positional. So it's not completely positional because the ordering of the terms don't matter, but clearly you can't permute the order of x and phi. So some positions matter, but not all of the positions are equally important. Okay, so so far we're just reviewing polynomial algebra. This is something we know well, how to improve on polynomial algebra. So before I start talking about improvement, I want to emphasize that I cheated. Somehow I cheated. Now I'm going to be honest about my cheats. So I cheated because the goal was to encode numbers. And the argument is I can encode numbers using polynomials with coefficients 0s and 1s. However, if you look very carefully here, I'm using numbers again. So if I want to use numbers, and the coefficients should be 0s and 1s, the alphabet should not include numbers. So somehow I have to get rid of these numbers and make everything seem like I'm not cheating. All right. So I thought the easy thing to do is to simply recurse. So I expand this as a polynomial, I expand this as a polynomial, and I keep doing this until I no longer have polynomials. So I no longer have numbers. So the alphabet I'm going to be working with, I already used this one. Let me use this one. So here's the alphabet. The alphabet should be the letter 1. This is for 1. Plus, I'm allowed to use plus. I'm allowed to use the exponent. And I'm allowed to use my symbol x. that you should think of as the number 2. So let me recurse for this number here. The number x to the power 4, this one, x to the power 5 plus 1 plus x. So this is going to be the number, the expression, so this number here, x to the power 5 plus x plus 1. I'm going to associate with that number the following expression. X to the power x, all right, x plus 1, and, right, plus 1, plus x plus 1. All right, so I had 5 here, and I say you're not allowed to use 5. So you should substitute 5 by 2 to the power 2, so to do all the steps. So this is 2 to the power 2 plus 1, but then you're not allowed to use 2. You're only allowed to use x. So here's our expression. So I was happy thinking about this, and it was brought to my attention that Reuben Goodstein had been thinking about this in 1944. So in 1944, he came up with this recursive encoding to deal with a problem that I'll mention in the end. Okay.
But so, you discovered it.
Yes, but I give him credit. I mean, what he was able to do with this is pretty surprising. So Goodstein called this hereditary encoding base 2. And it turns out you can do it in any basis. Right, so 2 is convenient because the alphabet is as small as possible. So is it good so far? The basic algorithm is encode your number base 2. Now if you're using polynomial instead of these bits, you can skip the zeros. And let me show you a number for which this makes a huge difference. All right? So,
do you consider the expression on the right-hand side as a polynomial?
Oh, so this one, no, this is no longer a polynomial. Okay. I don't. So this is expression. I'll call it exponential expression. Yes?
So in the binary representation, you have like 6 is the space you take, right?
Yeah, so yes, the number of bits
is much more than what you take there, right?
Right, so if I was to write a program to write this, you would say the storage here required is log n. And here, I'm going to measure the storage, fortunately, by the string, the length of this string. So this is the string in your computer that you write, if you were writing this into Maple. And the length, I'm going to essentially measure the length of this string. And let me show you an example where writing things this way makes a huge difference. So suppose you were writing the following number. So maybe I should erase this for now and write a number. So you wrote x to the power x, to the power x, to the power x, to the power x, to the power x. Okay, so exponentiation is not associative. So it's very important I specify in which order I'm doing these exponentiation, and this is my order. So I would argue the string here has length 1, 2, 3, 4, 5, 6. You need the exponents. So it's 6 times 2. But if you were to write this in binary, you would have a whole lot of zeros in there. So presumably, if your number is small, if you're encoding this in the binary system, you're beating this system because the exponents seems to take a lot of space. You are going to need log star n to encode what's happening in the exponent. But as soon as one of the terms starts becoming very large, you start doing slightly better than the binary encoding, but not systematically. Because if you had a lot of terms here, you would be worse than the binary system. All right, so that's the warm-up. The warm-up was Goodstein looked at the binary encoding. He was looking at a problem in logic, but already here we see that we're getting close to the goal of kicking 0 out, and it's making some strings at least shorter than the binary encoder. Can we do better? So that was the general question. And I'm going to argue that you can. And there's a second take-home message that we want to keep here, is that I realized that you should really think about number theory as writing programs. And here's why. So suppose I was to give you a very long string, and I told you that it is encoded in this format. So let me give you a short string as a warm-up. Let me say I wrote this. X to the power x plus x to the power x plus x plus 1. All right, so I say this is my number. This is what I input. And I ask, is this properly written? Is this a valid string encoding a number? So we want every number to have a unique string and every valid string to encode a unique number. Otherwise, we don't have a proper encoding. So there has to be a way for us to recognize whether a number is written properly. All right? And I think of this as compiling a program. So you input a program, the computer checks whether your program is written properly, and only once it's checked that everything is okay, it goes and executes the program. So how do I look at this and conclude that this is written properly? Well, so I'm going to argue this is not written properly. The reason it's not written properly, I have two terms that repeat, and in base 2, you don't want to have the same basis, so the proper encoding should have been x to the x plus 1 plus x plus 1. All right, but what was the rule? How did I know that this wasn't written properly and there's a proper way of writing it? So let me write the rule. An expression is written properly, so the compiler doesn't complain. If the number, so the expression is sum of x to the fk, okay, and k has to be, bounded, or 1 plus sum k less than n x to the fk. So either of these is fine. So this is when it's even, this is when it's odd. And the argument is that a number n is written in canonical form. So n is in canonical form. If all the fk's are distinct for different values of k, so all the if you have terms, they shouldn't repeat. So for different terms should have different exponents. And furthermore, the fk's themselves have to be written in canonical form. So the definition is recursive. So it's a sum of terms which are distinct, and the exponent has to be canonical. All right? So your compiler essentially looks at every term and says, is term 1 the same as term 2? Is term 3 the same as term 4? And so on. And if they're all distinct, it goes up and checks in the exponent, is this written in canonical form? So there is a criteria, and it's polynomial time to check whether your number is written in canonical form. So it can be done efficiently.
FKs themselves are written in the form n?
Yes. So fk, let me write it down. So fk and fk's are in canonical form. So it's a sum of distinct terms where each one of the fk's are distinct, and the fk must themselves be written in canonical form.
The base case being?
So the base case being x, so the 1 is 1, so when there's no term, and 2 is x. So these are your base case for the canonical forms. All right? Okay, this I am borrowing all the machinery from base 2. The fact that this decomposition exists is a consequence of the fact that every number can be written uniquely in base 2. Right, so there's nothing new so far. So now let's start talking about how we would improve this. Base 2 notation, we know from elementary number theory, essentially follows from the division algorithm. Very old division algorithm. That every number, if you divide two numbers, there's a unique way of writing them in terms of a quotient plus times the divisor plus the remainder. So that gives you the base 2 encoding. If we want to do better, we need to use another basic fact of arithmetics. And what I'm going to use is the fundamental theorem of arithmetics. It says every number can be written uniquely in terms of products of primes. All right, so what I'm going to talk about now is the prime hereditary encoding base 2. So I say base 2. Remember, in the Goodsteing encoding, you could use any number. But in the prime encoding, it's very important that the basis be a prime number. And I'm going to explain in a second why do you need the basis to be a prime number. And for convenience, if you want your alphabet to be small, well, pick the smallest prime. So what is the alphabet we're going to use to encode our numbers? So there will be 1, there will be x for 2, there's going to be exponent, there's definitely a need for multiplication. So let me write dot for multiplication. And we'll be done. Okay, so how does this work? And why in the world should this be better than the decimal encoding? So here's how it works. Let's actually look at 45. Yes?
And what's the dot? The plus?
Oh no, this, so definitely there is a plus. We're going to need plus, and we have times. Thank you. The dot is multiplication.
Oh, okay.
Yes, we're going to have plus,
Yeah.
definitely. So if I want to factor 45, so this quiz, 45 in prime factors, what does that give? All right, so this is 3 times 3 times 5, which is 3 squared times 5. 3 squared times 5. Okay, so there's nothing base 2 here. How do I get base 2? Right, so presumably, every number n can be written uniquely as product of pk to the alpha case. How do I get base 2? Now here's the trick. Here's an important trick we're going to use. So the trick we want to use essentially is going to benefit from the fact that, you know, its prime numbers are somewhat rare, and next to a prime number there's always a composite. So let's take the concrete example of 7. So if you take 7 and you subtract 1 from it, you get a composite, right? So 7 is 6 plus 1. But then you are in luck, because this is a composite, you can factor it in terms of primes that are smaller than that number, right? So 6 is 2 times 3. 2 times 3. All right, so now I want to work in base 2. I'm happy that I see a 2. So every time I see a 2, I am substituting the 2 by an x. But 3 is greater than 2. I do exactly the same trick. I say, well, 3 is 2 plus 1. And I add 1. So what I used here was the fact that next to every prime, there's a composite. And I can factor the composite using primes that are smaller than the number. And eventually, I'm going to hit a prime that I'm going to hit 2. If I keep doing that, I'm going to hit 2. All right? So that allows me to express the primes, at least, in terms of x times something, and eventually I'm going to have to add 1. There's another thing which is interesting. I have to somehow take care of the alphas. But the alphas are numbers. So let's say that I was looking at 7 times 7 to the power 5 times 11 to the power 7. The argument is, now that I have exponent, I can actually do the same trick to the powers. And recursively express these in base 2, express these in base 2, using recursively the prime encoding. All right. Now, why should this be shorter? Okay. Now we're going to get to why this thing should be shorter. So, to understand why it should be shorter, we have to understand the algorithm which actually recognizes that a string that you inputted in the second canonical form is valid. So if I write a string, let's say I write something like this, plus 1 times x plus 1, is this a valid string? How do we know? Well, here's the rule. Here's how you find out whether a string is valid. So a number is written, so n is in the second canonical form, if n is equal, the expression n is a product. So you see, I traded the sums for products. Product of a bounded number of terms of 1 plus fk's to the power gk. And now I'm going to recurse. So it's either this or x times, so this is x, times the product for evens, x to the g0, 1 less than k, less than n, 1 plus fk to the power gk. Okay, so let's explain what's happening here. Absolutely, what we want is that the factors are prime numbers. So this expression here should better be evaluating when I plug in 2 to a prime. And the rule is fk itself has to be fk and the gk's have to be in the second canonical form. All right. So the definition, just as for the first one, is recursive. And what we're winning here is that the products tend to have less terms than the sums. So if you look at a typical expression, and I did some experiments, so we're ready to actually look at the experiment part of the talk, the products tend to have significantly less terms than the sum. It turns out if you expand the sum, if you expand the products, then the size of the strings start being the same. So what we're winning is the fact that expression with products that are not expanded tend to be much smaller than the corresponding expression when you expand out the terms. All right, and there's x, so 2 appears on both sides. So how big can this difference be? All right, so this is where we actually need to be looking at some experiment, suggesting that something interesting is happening here. So let me turn on the projector.
So you save space, but to do integer factorization may take a while.
So that's a wonderful point. That's a wonderful point that I ought to address in a minute. So let me...
No, it's nice to save space, but...
So if you are somebody like Sloan and you're managing a database of sequences where you're unlikely to add sequences and manipulate them, I would argue you want to encode your numbers this way. However, if you are in the business of adding, multiplying, and so on, you pay a huge price because addition becomes as hard as factoring. Right, so then the question is, how do you encode these numbers? If you were to create a database of these, how would you do it efficiently? You don't want to go factoring every number one by one to find the recursive encoding. And it turns out you can do it better than the factoring. How do you recognize? Thanks to the the AKS algorithm, you can test for primality efficiently. But we don't know yet how to factor efficiently. So let me turn on the projector and start getting a sense of how far we can go with this. So it's on. I can see that the projector is lighting up. So that's good news. And I'm seeing something on the screen. So that's a good sign. But I'm not seeing my computer yet. So. Change the source. This is the so-called Murphy's law.